Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to calculate the pH changes in a buffer solution. So this is the kind of problem where you have your buffer and you're either going to add a strong acid to the buffer or a strong base. And so when you do that, the way you solve that kind of problem is you have to break it up into two parts. There's going to be the stoichiometric calculation part. That's where you have to calculate how much of the conjugate acid or conjugate base that's reacted, figure out what's left over at the end of that reaction, and then the second part is then do the equilibrium calculation like you would normally do. So the first part, again, is to do the stoichiometry calculation. So we're going to be looking at a buffer where you have the acid with the conjugate base. And so if you add a strong acid, that strong acid is going to react with the conjugate base and react with it and remove it, creating more acid, the weak acid. Or if you add a strong base to the buffer, then that strong base is going to react with the acid part of the buffer, and that's going to decrease the acid and increase the conjugate base. And so you've got to do that calculation first, and then once you figure out what the remaining amounts are after that reaction occurs, then you are going to do the equilibrium calculation where you calculate the pH based on the new amounts of your acid and conjugate base. And so that is the same as what you've done already with regard to weak acid and weak base calculations. And then prior to this, in my previous video, I showed you how to calculate the pH of a buffer. So that part would fall under part 2. So let's go over an example so I can show you what I'm talking about. So here, let's start with a 1 liter buffer solution. So I have a 1 liter buffer solution, and here I have a 0.100 molar solution of my acid, my weak acid. So I have a generic weak acid here. And along with that, mixed in is a 0.100 molar concentration of the conjugate base. So this is my buffer here. And so what we've learned before is that whenever you have equal amounts of your acid and your base in the buffer, then basically that means that the H plus concentration is going to be equal to your Ka value. And that also means that the pH is going to be equal to the pKa. So here right now, the pH is equal to the pKa. Let's see what happens when you add an acid to it. So we're going to add 0.025 moles of a strong acid. Basically, it's going to be H plus. So remember, strong acids ionize completely in water. So basically, the amount of acid you're adding is going to be the same as the amount of H plus you're adding. So I'm adding H plus. This H plus is going to react with the conjugate base. So it's going to decrease the amount of conjugate base and create more acid. And so that's what I have here. So so the first part you want to do is the stoichiometry part to figure out how much of each of the species you have, your acid and your conjugate base, after the acid has completely reacted. So for the first part, you're going to do the stoichiometry problem. And here we're going to do what is called an ICF table, not an ICE table. So remember, ICE tables are only for equilibrium problems. This is not an equilibrium problem. This is a stoichiometry problem where you got something that's going to react completely. So here I'm adding the H plus. So my strong acid is the H plus. That's going to react completely with the conjugate base, and it's going to form HA, which is my generic weak acid. So the ICF table stands for, of course, I is initial, C is change, and F is final, not equilibrium. So what's the final amounts? So initially, before I added in the acid, I have zero amount of H plus, or approximately zero, because this is a weak acid, so it's not going to ionize very much in water at all. So we can assume that it's going to be approximately zero. And then I have for my conjugate base 0.100 moles, and I have for my acid 0.100 moles of my weak acid. Now, you'll see that I am using moles here instead of molarity. It's just easier to work with moles here because it's the moles that are reacting together, so we can figure out what the stoichiometric amounts are. So we know that from here, 1 mole of H plus will react with 1 mole of your conjugate base, A minus, and that's going to create 1 mole of HA, your weak acid. So we can use moles to figure out what the stoichiometric amounts that are going to be reacting together. Okay, so I know I'm adding 0.025 moles of my strong acid, so the change is going to be, I'm adding 0.025 moles. So that's it. So there's nothing, I'm not really doing anything with this here. So I'm adding this amount of my H plus, my strong acid. And so what I know is this amount of my strong acid is going to react completely with my A minus. So in the end, my final amount of H plus is going to be 0 again. So this is going to be 0. So I end up with 0, but I know that if all of this reacts, it's a 1-to-1-to-1 ratio. So if all of this reacts with my A minus, then that means 0.025 moles of this will be gone. So basically, I'm going to be subtracting out. So this is going to be minus, this is going to be gone. So this is going to be 0.025 moles. So I'm going to be subtracting that from 0.100. So then this becomes 0.075 moles. So I'll have that many moles of my conjugate base left over. And then since 0.025 moles of my conjugate base reacts, that's going to form the same amount of weak acid. So that's going to be adding to this 0.025 moles of my acid. So that's going to end up being a final amount of 0.125 moles of my weak acid. So I've now finished the stoichiometry part of my problem. So now at the final amount I have, this is before I do any equilibrium. So the final new amounts that I have, the new amounts of acid and conjugate base, is going to be 0.075 moles and 0.125 moles of the acid. So now I'm done with the stoichiometry part. I can go to the equilibrium part. And so now when I go to my equilibrium table, it's very important to switch back to your concentration. So I've been working with moles here. And in this problem, we're assuming that the amount or volume of the strong acid that I've added is very small and doesn't affect the overall volume of 1 liter. So we'll assume that it's pretty much 1 liter at this point. But that may not be true for other problems. So if I take, if I have, a relative amount of a smaller amount of buffer, and if the amount of acid or base I'm adding does change the volume a bit, then you want to refactor that in. So you would want to take the number of moles you have, divide that by the new volume after adding your acid or base, and then put the concentrations in your ice table and work with the concentrations. But since we're assuming here that the volume hasn't really changed much after adding the acid, we still have 1 liter. So if we divide these by 1 liter, you get the molarity. So the numbers stay the same. So here now what we can do is we can go to the equilibrium problem. And so the equilibrium problem, again, since we're working with an acid conjugate base buffer, we have the weak acid reacts with water to form H plus ions and your A minus, your conjugate base. And so now we can take these values and plug them in here. So initially for the equilibrium, we're going to have A minus is going to be 0.075. So that's going to be 0.075 molar, right? And we have here for HA is 0.125. So that's going to be 0.125. And again, that's going to be molar. And then we're ignoring water, so we don't care about water. Water's not in the equilibrium expression, so we're Xing that out. And then the H plus initially, again, because this is a weak acid, we're going to say basically it's approximately 0, effectively 0. So now what you would do is you would do your equilibrium problem. So when you're doing the equilibrium problem, you can either do an ice table and do the X is too small approximation and see if that works, or if not, you could use the quadratic formula or do the method of successive approximations, or you can do the Henderson-Hasselbalch equation, HH equation for short. So either one would work fine if the X is too small approximation is valid, okay? So in this case, I'm showing the ice table to make a comparison with this one. So until I would do ice tables first and get really good at those before jumping to your Henderson-Hasselbalch equation, because this will give you a feel for like when is it a good time to do the Henderson-Hasselbalch equation. And normally it really depends on how concentrated or how dilute your buffer is, and things like that. So, and it also depends on your Ka value. So if your Ka value is kind of large, then maybe not. So the two things you want to be looking for is a small Ka value and a fairly concentrated solution of your buffer. Those are the two situations you want to be in. And normally your concentration of your acid should be about 100 to 1,000 times greater than your Ka value, and that's usually a good rule of thumb. But it's going to depend on the specific problem itself. So just be aware of that. So here I have my initial conditions, and then I'm just going to do my ice table. So here, since I have 0 here, I can assume that it's going to go in this direction. So here, because again, Le Chatelier's principle, I have 0 here. It's going to want to go in here to kind of create product there. So that means I'm going to have a negative X here, and then this is going to be a positive X, and this will be a positive X amount that I'm going to form. That means that this is going to be 0.125 minus X. This is going to be X, and this is going to be 0.075 plus X. And so then I would set up my equation like I normally do. So the Ka is equal to the H plus concentration multiplied by the A minus concentration over H A concentration. And so this is going to be X. This is equal to X times, and then we have 0.075, 0.075 plus X over 0.125, so 0.125 minus X. And then here we can assume the X is small. We can assume that and do approximation. And so you would get rid of the plus X and minus X. And so this ends up being Ka is equal to X multiplied by 0.025 or 75 divided by 0.125. And then you can go from there and find X. And then X would be your H plus concentration. And then verify that that is valid due to the 5% rule. If so, then you can use the negative log of the H plus, which is X here. So your X that you're solving for would be your H plus concentration, and then you could take the negative log of that and you would get the pH. Okay, so that is in general how you would solve a pH change in a buffer solution after adding a certain amount of strong acid or a certain amount of strong base. Now with a strong base, it would work exactly the same, except for this time, for your calculation here for your ICF table, there you would need to do a reaction where your hydroxide, if you're adding a strong base, you're going to have hydroxide reacting with your conjugate base or with your conjugate acid instead. So what you would end up with is the equation OH minus aqueous reacting with your HA, your weak acid, and then that's going to form water. So you got H2O liquid plus, and then you got your A minus left over aqueous. So instead of this equation where you have a strong acid reacting with your conjugate base to form more acid, here you're going to have your strong base reacting with the weak acid to form more conjugate base. So you would do that first, do the stoichiometry first, and then once you figure out what your final amounts are, then you would do the exact same thing over here. So the only difference is if instead of a strong acid, I added 0.025 moles of a strong base, then what would happen is I would end up, instead of 0.075 moles of the conjugate base, I would actually end up with 0.125 moles of the conjugate base and 0.075 moles. So these numbers would be switched because when I'm reacting a strong base, I'm reacting that with the weak acid. That's going to decrease the amount of weak acid and therefore increase the amount of conjugate base I have. But then the numbers are going to be switched here. But then when I do my equilibrium problem, again, I have the same choice. I can do an ice table like I normally do, or I could use the Henderson-Hasselbalch equation. I hope this is helpful. If you enjoyed this video, if you learned something in this video, if I helped you clarify some stuff, please make sure you hit that like button and subscribe to my channel. Hit that notification bell right up there, right up there somewhere. And, that way you could be notified by other videos that I put out. Please put a comment down in the comment section below. Let me know what you think and if you have any comments or questions. Thanks for joining me. Have a great day.